Hi everyone. I just thought I'll just revise some quick points, and for those of you who felt the previous class was a little fast, I thought I'll give a very brief idea about how to I mean what you can expect from the exam, and how should you prepare for it. Uh, so first, I have discussed about receivers mainly, and also a little bit about transmitters. And so in the exam, you'll have to just apply your concepts and ideas. I mean, it's not very difficult, but if you understood the basic concepts. So for example, in receivers mainly we discussed about noise figure, how to find noise figure given a circuit. So I told you one of the easiest trick is, especially with circuits with very high input impedance, just find the input referred noise for the circuit and then divide it by the 4 kT RS. I mean, here RS is the source resistance or the antenna's radiation resistance. So I have already used the word antenna radiation resistance. It's also the source resistance for the circuit, and then just add 1 to it. So this will give you noise figure in watt per wire. I mean, it's a ratio of two quantities, which is actually watt by watt. Okay, noise figure. Essentially, you can look at it as, in this case, if you look at this equation, it tells you it's watt per watt. But if you come from the definition of noise figure, it is actually SNR at the input by SNR at the output. Now we know signal to noise ratio is essentially the power ratios of two quantities, signal power by noise power. So the units will be watt by watt divided by watt by watt. So the unit of noise figure will be in dBs. Okay, and we know noise figure, if you look at this result, here I have assumed 4 kTRS is a spectral density is constant as a function of frequency, but VNI square can be a function of frequency. So therefore noise figure will be a function of frequency. Again, these are all well known points, you can find it in the textbook as well. Okay, yeah. So next thing, when we talk about a receiver, an antenna, immediately following an antenna we have a band pass filter for linearity. Mainly the band pass filter is present mainly to filter out interferers. So in RF system you also have a signal and a strong interferer. Normally we want to filter out the interferer, so therefore we need the band pass filter. Following that will normally be an LNA, a low noise amplifier. After that we will have a mixer which will down convert the data. So your data will be centered around a carrier frequency. We will multiply this with a carrier frequency, and the data will be down converted to a low frequency. Then finally we will have a baseband filter, BBF, and BPF is a band pass filter. I have already used this terminology, so I might use it in the exam as well. This baseband filter is eventually fed to an ADC. So this is a normal receiver structure. Transmitter will be the inverse of this. So first, if you take a transmitter, so we'll start from, see here, this is digital data right now. So I'm mostly the communications we will be dealing with is digital communications. But in the course, what we'll be discussing is the analog part of communication. So till this part, when I said this is where the analog to digital conversion takes place in a receiver. Okay, we are concerned with the analog part. So from the band pass filter to the LNA to the mixer to the baseband filter. So this entire thing is the analog part or the RF part, RF and analog part. So this is what we are concerned with this in this course. Okay. So similarly in the transmitter you have a digital data. So first you will need a DAC, digital to analog converter, which will convert your digital data to analog data. This analog data will then be passed through a filter, BBF, called the baseband filter. Okay, this filter output will be fed to a mixer or up converter. Here I am assuming amplitude modulation, so I am showing the symbol of a mixer. It can also be frequency or phase modulated. The transmitter will be slightly different in that case. Then you multiply this with a carrier. So this is data is now the Fourier transform here will be centered around DC. After the mixer operation, the Fourier transform will be centered around FC. And this data will be then passed through a power amplifier. This power amplifier will eventually connect to an antenna. So this is your transmitter. Again, when I say transmitter, we are concerned about the analog part of the transmitter. So from the baseband filter, mixer and power amplifier. Usually RF, I mean these DAC can also be part of, I'd rather use the word analog for this, and this is RF section. Whenever you are going for gigahertz of frequencies, that becomes the RF section. Okay. So I also discussed a very important term called sensitivity. If you understood noise figure, so noise figure is nothing but it's a measure of how much your SNR degrades as you pass a signal through an amplifier, right? So first you measure the signal to noise ratio, maybe with respect to some source resistance, Okay, if that's your signal to noise ratio, when you feed it to an amplifier, at the output you are going to get a different signal to noise ratio. The difference between the two in dB. So for example, if I express noise figure in decibels, normally noise figure directly, by definition noise figure is simply the ratio of SNR at the input divided by SNR at the output. So if I ask you to find the noise figure in dB, you can simply do signal to noise ratio at the input, express it in dB, minus signal to noise ratio at the output, expressed in dB. Again, you can express a quantity in dB if it's a ratio of two similar quantities. Like in signal to noise ratio, it's power to power, signal power to noise power. And I also discussed another very important parameter called available noise power. Okay, it is that power. So for example, you are receiving a signal through an antenna, you are receiving a signal, and antenna itself generates noise because there is radiation losses in it which will generate noise. And we said that can be modeled. So for example, this is Vs is the signal, and we also have noise in series with it connected to a source resistance. So if I apply the principle of superposition, I can find what is the power delivered by Vn. Okay, that's going to be Vn square upon Rs, 4Rs. That's the maximum power delivered by that maximum power that can be delivered to a matched load. Okay, this is the maximum power you can deliver. Similarly, for the signal, it's going to be Vs square by 4Rs. Now we will talk about this term. So this is Vn square by 4Rs. Now I'll take this in Fourier domain and then say that Vn square is simply 4 kTRS divided by 4Rs. Okay, see power as a quantity, when you find this is actually when you see Vn square, if I take it to Fourier domain, okay, so I can simply say that this is little bit more complicated than what I'm directly using. I'm saying Fourier domain directly here. You have to actually compute for power as autocorrelation function and all that. I'm just directly quoting the final result. Vnf square, it's simply, I'm just saying we know what is Vn square. That's 4 kTRS upon 4Rs. Okay, this is the units is volt square per hertz. Vn square, normally the units is volt square per hertz for a resistor, noise, for a noise signal. When you divide it by 4Rs, the units will become watt per hertz. So this is the important thing here. Now if you look at this number, it is kT. kT is the available noise power, or the power that a noise can deliver to a matched load. Now if you look at this number, it is independent of the source resistance. Okay, that's a very interesting result. It's actually independent of your source, the resistance for which we found, the resistance which is generating the noise, it's independent of that itself when I find the available noise power. Okay, and if I ask you to compute the noise power itself, this is available noise power in hertz. Noise power itself, then it will be simply kT into B. So this is your, B is your RF bandwidth. So I'm just assuming the positive bandwidth is B. And here if you see, I have used 4 kTRS. So it's actually one-sided spectral density. So whenever you have one-sided spectral density, you can just use only the positive bandwidth to compute the power. Okay, so this is your total noise power, kT into B. Now we know that what happens, what did we discuss is that, so say for example, your signal to noise ratio at the input is some factor, say is Ni, and it's passed through an entire receiver chain. The receiver chain might have amplifiers, mixers and so on. And when the signal comes out of this, the signal to noise ratio is going to be SNR at the output. Now noise figure here is a very useful metric. It's a very interesting metric. What it tells you is that it tells you by how much your noise increases. So if I know the input referred noise before I feed it to the amplifier is, say, Pn is the total input referred, or the total input noise power, then for you to find the output noise power, you just have to multiply Pn into Nf. Okay, so it sounds quite intuitive because, see, for example, noise figure captures the noise added by this stage. It also includes the noise at the input N. Okay, it tells you by how much the noise had actually increased at the output. Okay, so therefore, so for example, I will show it graphically. So if let's say kT is the available noise power, you multiply it by B, this is noise power per hertz, multiplied by B, you will get total noise power. Okay. Now, a noisy receiver will add some noise to this. So that will, if I multiply this, so let me call it Pn. If I multiply Pn with noise figure, I am going to get the increased noise level. Okay, so noise figure, in a way you can see it as a metric which tells you how much it's a ratio, it's actually a ratioed quantity, it's not a real, it's not a noise in itself. But when you multiply it by power, you see how much does the noise actually increase. Okay, so if I give you the input noise power, that is available noise power, and then ask you to find how much does the power increase, noise power increase as it goes through the receive chain, you can simply multiply it by NF. Okay, so NF here is the input referred noise figure, the total noise figure of the system. You just have to add it to this, or multiply it with this. Your signal power will remain as it is. If the receiver was noiseless, say for example, I will go back to this, let me just, if the receiver was noiseless, you are receiving the signal power and then you are also having some noise power. Both of them are going to go through a certain gain, A by A, right? So the output, you are going to receive P signal by P noise into A and into A. So A and A would, see there is A square and A square, because I can write, actually let me write power gain instead of using A. If in case of voltage gain, it can be A square, but I'll use the word power gain, so it will simply GP by GP, same power, both of them see the same path, so they will see the same power gain, GP upon GP. So you are going to get ratio of signal to noise ratio at the output will be same as the signal to noise ratio at the input. Okay. So if there was no noise in the receiver, the signal to noise ratio at the input and output will be same. Noise figure will be 1 or 0 dB. Okay. Noise figure in dB, when you express it, it's going to be 0 dB. Normal value, it's going to be just 1. Okay. So if I want to find the increased noise at the input, I just have to, when I multiply it by noise figure, because noise figure is always greater than or equal to 1. This is another important result. So noise figure actually captures by how much your available power or the noise power increases. So that's why it's a very useful metric. So from that we can compute P signal by Pn av into NF. So this will be your signal to noise ratio at the output. Okay, if you just know your noise figure and signal power as well, so then we can measure this. Now lastly, in the last part of the lecture, I discussed a very important quantity called as sensitivity. Now what is sensitivity? Sensitivity is the minimum signal level that a receiver, an RF receiver, can sense and make a reliable judgment. For example, you are transmitting some ones and zeros. Let's say you multiply it by a carrier, so it's ASK, amplitude shift keying. Now this signal level might be very, very low here as it comes to the receiver. And as a spec, I'm going to say I need a bit error rate of certain PE. This is the bit error rate. Now from your basic communication theory, we know that the bit error rate, there is a graph which relates bit error rate to the signal energy, EB by N0. There is a graph which says N0 is the thermal noise level that you are adding, and EB, probability of error, actually goes down exponentially as you increase your signal to noise ratio. Okay. So normally the spec comes from this. So for example, if I give you probability of error of 10 power minus 12, which means in 1000 billion bits, so or 10 power 12 bits, you can only have one bit of an error. You can have error only in one bit. Then you should know, you will mathematically calculate what is the EB by N0 necessary for that. Now this EB by N0, if you have learned digital communications, it comes from the simple mathematical model of the channel as Y equals X plus N. Now where does this come? This is an RF receiver, we are talking about analog signals. Where does this come from? So in a receiver, if you see, the antenna receives the signal, it undergoes through a band, it goes through a band pass filter, then an LNA, a low noise amplifier, then a mixer multiplied by the carrier. The output of this signal, this is what I am drawing here is a 0 IF receiver, meaning there is only one step for down conversion. Then we have a baseband filter, and finally this data is fed to an ADC. Okay. Now you should understand, at every step we are adding noise. Noise is added to the band pass filter, noise is added by the low noise amplifier, mixer will add noise, this filter, analog filter will add noise, ADC will also add the noise. And you're receiving a signal power, it's undergoing gain and all that through the chain, but it's also getting added, some noise is getting added in the channel, in the chain. Finally, when the data is digitized, that is where you have to meet the EB by naught spec. So at this point, when I measure the signal to noise ratio, that should correspond to this value. So that signal to noise ratio, which the digital logic, the digital receiver is going to see, that will dictate your probability of error. Because the decision making is done by the digital block. If you remember what is decision making, any digital communication system, whether the bit is 1 or not, someone has to take a decision there. Based on the output, you will make a decision. That decision is made by the digital block. We can also do it in analog way, but conventionally I am saying that decision is made in the digital block, and therefore the EB by are not necessary at the ADC output or at the ADC which is what will determine your probability of error. Okay. So said in other words, in analog domain, I'll say there is a certain signal to noise ratio that the ADC should see. I mean, I'm going to input refer the noise of the ADC also. If you have done the basic course on mixed signal design, you will know how to find the input referred noise of an ADC. The sampling switches, the sample and hold circuit, the preamplifiers, everybody is going to contribute to some noise, and you can input refer it. That signal to noise ratio is the required signal to noise ratio for reliable communication. When I use the word reliable communication, what I mean is the probability of error is met. So if you need a probability of error of say 10 power minus 6, which means out of 1 million bits, only 1 bit can go wrong. 1 in 10 power 6 bits will go wrong. That's what it means. So this is the signal to noise ratio required necessary at the output. Okay. Now, how do we find, given this knowledge, I know the signal to noise ratio at the output. Okay. And for any receiver, to talk about the noise of a receiver, we told we will use the word noise figure. Noise figure captures the noise information of the entire receiver. I can find the total noise figure of the receiver. So what I'm going to do is, I'll just show this entire as an RX chain, the receive chain. I'm going to model the entire noise at the input. Okay. Or let's say I give you the noise figure. I have given you the noise figure. Then all you need to do is just multiply the input noise power into noise figure. That will tell you the overall noise you are going to add to the signal. So this will be Pn into noise figure is going to be the input noise that you are going to add to the signal. Then signal comes as it is here. Okay. So the signal to noise ratio at the input is going to be, the signal to noise ratio, if I find the signal to noise ratio at the output, it's simply now the RX chain, they are both going to see the same gain. So P sig by Pn into noise figure will be your signal to noise ratio at the output. And this is something we are aware of, right? So if I don't include noise figure, that doesn't include the noise of the receiver. This Pn will then only be the noise of this channel radiation, the antenna radiation resistance noise. To include the receiver's noise, I'll have to multiply it by noise figure. Again, this makes intuitive sense. We just discussed now. Okay, noise figure captures by how much the noise increases as it passes through the RX chain. Okay. So I'll discuss it graphically. So we said this is KT into B. That's your thermal noise power because of the radiation resistance, right? That's going to get added to the signal. Then once you connect it with the receiver, you will have to add KT into B into noise figure. So that's the increased noise because of the receiver. So if I want to express all this in dB, I'm going to write KT 10 log of KT. So KT is watt per hertz. I already told you if you take 10 log of KT, you're going to get minus 174 dBm per hertz at 300 Kelvin. So this value is at 300 Kelvin. So plus I'm going to write this result like this, plus 10 log of T by 300 Kelvin. So this result, which also includes temperature in the equation, plus 10 log of T by 300 Kelvin, plus 10 log of B, the bandwidth, plus the noise figure in dB. So noise figure we normally take 10 log. So this will be noise figure in decibels. So this is the total noise that you are adding to the stick signal. Okay. See, noise figure already captures the information about the noise you are adding. Okay, now I can assume the receiver is noiseless. Okay, so once I include the signal to noise ratio, see, for example, let me just draw it in a more clear way. So first you have a signal that is entering the antenna, and antenna is going to add some noise level. That noise level is going to be kT into B. Okay, the power of that noise. This, now what should I do to this is, I should now include an extra noise which will be Pn into noise figure minus 1. Okay, so Pn into noise figure minus 1, NF minus 1, NF I told you minus 1 is told you the excess noise that you are adding. Okay, this is now going to be fed to the RX chain. Finally, this will go to the ADC. I'm going to compute, let's say ADC, I've also included the ADC's noise here in the RX chain, and finally it will be converted to digital bits. Let's say I've included ADC also inside this. You get the digital bits here. Now if I measure the signal to noise ratio at this point, see, if I consider only signal, the signal to noise ratio is infinity here. At this point, the signal to noise ratio is going to be P sig, that's your input signal to noise ratio, by KTB. At this point, it's going to be P sig by KTB into noise figure. Because you have ordered this noise and this noise, both of them will add up, that will simply be Pn into noise figure. Okay. Now I'll call this as some SNR X, SN S by N X. Now this is the noise figure at the output. That's going to be exactly same as SN by X, because you know both of them are, both the signal and noise are going to see the same transfer functions. So here SNR at the output will simply be equal to SN at this X, that is the input. So noise figure, once you capture the effect of noise figure, you don't have to worry about the receiver chain. Okay. So now KTB into noise figure, okay, is the, into noise figure actually captures the excess noise. So I'll plot the noise graph now. So you've added a noise which is KTB. This is at the antenna input. Because of the receiver, this is going to increase by KTB into noise figure. And we already saw that how to express this in dB. At 300 Kelvin, I can write as minus 174 dBc per hertz plus 10 log of T by 300 Kelvin plus 10 log of B plus 10 log of noise figure. I'll write noise figure in decibels. Okay. So this will be the overall noise. Now we just said that whatever the signal power is here, this guy and this signal power, both of them are going to see the same gain at the output, right? So I'll simply measure the signal to noise ratio before I feed it to the RX chain. Once I model noise figure, I'll simply measure the signal to noise ratio at the RX input itself. Okay, that will be the same as the signal to noise ratio at the output. Now we just discussed from the bit error rate for reliable communication, the signal to noise ratio is normally mentioned. Say that value is some S by NO in dB, it's given to you in decibels. Now we have to add in dB to this. Okay, this value will be, so let me so now we'll have to add the signal to noise ratio to this. Now this level is going to be your signal level, right? So you have P sig by P noise tot, I'll call it P noise total, is your signal to noise ratio at the output. Okay. Now that is simply equal to P noise tot plus signal to noise ratio at the output, into. Okay, if I take decibels, if I take 10 log on both the sides, it will simply add P noise total plus this will be in dBm, it can, P noise total can be in dBm by signal to noise ratio in dB. If I take 10 log, you will get that. Okay. So if I add the signal to noise ratio to this in dB, S by N output at dB, the level I'm going to get here, that will be the minimum signal that you can apply to this receiver. Okay, of course, if let's say I tell you I don't care about signal to noise ratio, just blindly tell you what will be the minimum level of noise you can apply, you will say that signal power should be equal to noise power. At that point, you can no longer distinguish signal and noise. So it has to be obviously greater than KTB into NF. But there is also a requirement on bit error rate. It tells you, okay, I need 10 power minus 6 or 10 power minus 12, meaning in 10 power 12 bits I can only make one error. That puts an extra constraint. It tells you, no, you can't just be noise alone, you have to be more than noise by a certain amount. That's your signal to noise ratio of the output. Okay. When you add that, you are going to get this minimum signal level. So that's called sensitivity. That units, you can express it in dBm or it will be in watts. Okay. So if first I'll write it in watts, P signal is simply going to be, so first I'll write KTB into noise figure. So this will be your total noise power, that multiplied by signal to noise ratio at the output. So this will be your sensitivity, minimum signal power. Okay. Or you can also derive this result like your textbook does, Razavi's textbook does. It derives in a very simple way. Your noise figure is actually nothing but signal to noise ratio at the input by signal to noise ratio at the output. That's the definition of noise figure. So I'll write signal to noise ratio at the input equals noise figure into signal to noise ratio at the output. Now if I express this, a signal to noise ratio at the input is nothing but P sig by P noise. P noise is simply the available noise power KT times the bandwidth. That will give you noise figure into signal to noise ratio at the output. So the signal power at the receiver is simply NF into KTB into the signal to noise ratio at the output. So that's how you get this result. I just gave you an intuitive way of looking at the same result. From an engineer's point of view, it's much more intuitive. Here if I just blindly derived it, it looks like a textbook result. So that's why I gave an intuitive explanation. Okay. So here if you look at this graph, I didn't consider the receiver at all. Once I have the noise figure information, okay, I computed the signal to noise ratio before I'm feeding to this receiver. And I told you a few moments ago, the signal to noise ratio at this point, which I called it as Sn by x, signal to noise ratio at the input as Sn, signal S by n at x, is same as the signal to noise ratio at the output, right? Because both signal and noise are going to see the same transfer functions, so it will cancel out and you will be left with Sn, signal to noise ratio at the output will be same as the signal to noise ratio at the input of the receiver after you consider the noise figure. Okay. So this is an interesting result. Okay. So from this, that's how you estimate your sensitivity. So your sensitivity or the minimum signal that you can apply for reliable communication can be expressed as minus 174 dBm per hertz plus 10 log of bandwidth plus 10 log of noise figure. This is nothing but noise figure in dB. So if I can express noise figure in decibels plus signal to noise ratio at the output. Again SNR expressed in dB. This is your expression for sensitivity. Now the next question is dynamic range. I very briefly introduced what is dynamic range in the previous lecture. That's the maximum signal you can apply. P sensitivity, P sig tells you the minimum input signal level you need to apply it so that you have a reliable communication. Now what is the maximum signal you can apply? Now that is found, for example, I can use 1 dB compression point as a metric. There are many ways of defining it. One simple way is to use 1 dB compression point. So we know that what happens is that as you keep increasing your signal power, I'll call it P sig here, your gain will remain constant. Output signal power will also keep increasing. And after a certain point, instead of the signal power output signal power increasing linearly with the input signal power, it will start reducing. So we said that there was one metric we used, we called it the 1 dB compression point. So there we expressed 1 dB compression point as A1 dB. Okay, the units were volts. We expressed it in peak value, which was in volts. I told you we can also express it in terms of dBm as well, provided you should mention what is the ohm system that we used to represent it. Okay, but if I ask you in a question, express in volts, express it in volts. Okay, that's it. Or in dBm, express it only in dBm. Look for the question paper. In the question paper, look at it. What am I asking specifically? Just express it accordingly. Okay. So as I keep increasing the signal power, after a point the gain will start, the receiver will start saturating. The receiver amplifiers are all nonlinear amplifiers. It will start saturating. So when the overall received gain starts falling by 1 dB, then you will stop at that point. So that is determined by the 1 dB compression point of your receiver itself. That to your P sensitivity, Psen is your sensitivity, will be your dynamic range. So you have to express, or I can simply take 1 dB P, 1 dB compression point divided by P sensitivity. Okay, this ratio, dynamic range can also be a ratio, or normally it's expressed in dB. So if you take 10 log of this quantity, P 1 dB compression point of the entire receive chain, not just the LNA or any single ampere, but the entire receive chain, divided by the sensitivity, receive sensitivity. Okay, so this term is what we call dynamic range. There is also other way of defining dynamic range. I will not be testing this, but I will just quickly mention it. What we do is we feed two tones. I mean, minimum level is anyways known, that's your sensitivity, that we don't change. Maximum level, we feed two tones, two interferers to the system, and then measure the signal levels that come into the receiver, the intermodulation products. As you keep increasing these levels, the signal level also the intermod term also keeps increasing. Now when the intermodulation term levels become equal to the sensitivity, Psen, okay, when the intermodulation levels become equal to the sensitivity, at that point we stop it. Okay, which means if your intermodulation signals become as strong as the minimum signal your receiver can receive, then it will think, okay, I am receiving signal itself. Okay, it will think that way. So which is why we should at that point we should stop it. So that will be your maximum interferer power that it can tolerate. So we will note down the value of the interferers which you can feed to the system when the intermodulation term power becomes equal to your noise floor. I'll just clear it in the next lecture. It's either noise floor or sensitivity. I'll just clear that in the next lecture. So when the intermodulation power becomes equal to the sensitivity, okay, that I'll clear it in the next lecture. Okay, so this is other definition for dynamic range. See, minimum level is always fixed, which is P sensitivity. The maximum level can be found by using just a single tone or your carrier at the desired frequency, your signal at the desired frequency, and find the 1 dB compression point. Or you can feed an interferer, two tone test. This dynamic range is measured in a two-tone test, and then see when your intermod terms keep increasing and when they become equal to the input referred noise floor or sensitivity. That I'll clear it out in the next lecture. Okay, in the next video I'll immediately post it. Okay, so this is other way of finding the dynamic range. Okay, I'll stop at this point. Just go through all the things that we discussed in this video, and also you can go through chapter number, I'll probably send out a mail as to what to focus on. Chapter 2 in Razavi's textbook fully, almost everything we have covered in it. And chapter 5, which is the transceiver architectures, I'm not sure 5 or 4, I think it's 4. The transceiver architectures, just go through 0 IF, heterodyne receivers. Okay, I'll discuss about these two things in the next lecture, the next video. Go through this, okay, and just try to understand. You see, the problems necessary to solve in the test and all will just require your intuitions, understanding, good circuit analysis skills. Those are the things I'll be testing on. Okay, so that's it. That's it for this lecture. I'll discuss it in the next lecture. Any other points which I want to.